All right, continuity. This is AP, really encompasses AP Unit 1, Sections 10 through 13. This is a big piece of us moving forward and getting into derivatives. So there are three requirements for a function to be continuous at an x value. So imagine you have a function, and we're going to call this c. All right, so first of all, f of c is defined. So you must have a y value at c. So if you have a y value at c, you have reached the first requirement. 2, the limit must exist at c. Now for a limit to exist, of course, that means the limit on the left has got to equal the limit on the right. So I have a limit coming in. Let's say it goes to there, and on this side it comes up, and it goes to there. I have now satisfied the second requirement because the two sides are coming together, the limit exists. And now you'll see the third requirement is that the limit must equal the function's value. I have failed in that one on the graph that I've drawn. So I'm going to redraw this graph. In order to satisfy the third condition, I need the limit on the left to equal the limit on the right to also equal the function's value. So this gives me continuity. So some examples of graphs that are not continuous, well, you just saw the one that I drew, where the limit exists, the function exists, but the limit and the function do not equal each other. This is what we call a discontinuity at C. So we are discontinuous at C. We could have the limit existing and the function failing to exist. That is also a discontinuity at C. And then the third possibility is we could just have failure of the limit to exist. So this is failure of the limit to exist. And then let me just show you a fourth possibility here. Still failure of the limit to exist, but potentially at what we call vertical asymptote. So here's a vertical asymptote here. So this is also a place where we have a discontinuity because once again, the limit does not exist. All right. So just a point of clarification here. I'm going to go up to my first graph that's in black right here. This function has a discontinuity right here at C. It is actually continuous everywhere else. So we have continuity at all of these x values. We just don't have it at C. So this statement right here where a function is continuous on an open interval if it's continuous at each point in the interval. So for the graph I'll call A here, it is actually continuous over this entire interval and over this entire interval. It's just not continuous at C. Many functions are continuous everywhere, and we call those continuous functions. So the graph that I've drawn here, my prime example, that we would classify as a continuous function because it's continuous everywhere in their domain. And most of the functions we deal with on a daily basis are continuous functions. Polynomials, they're continuous everywhere. Rational functions, they're continuous everywhere in their domain. Now, if it like number 2 is not in the domain of this function, and therefore the function would be discontinuous at that point, but for a function to be classified as continuous, it only has to be continuous in the point in its domain. Exponential functions like 2 to the x, e to the x, they're continuous all the time. Log functions like log base 6, ln of x, they're continuous all the time. Trigonometric functions, sine, cosine, they're continuous everywhere all the time. Tangent has discontinuities, but it's at places that are not in the domain. So it is technically a continuous function, even though it has discontinuities. Just for a point of clarity here, this function down here has a discontinuity at what I'll call C, but it's still considered to be a continuous function because the point C is not in the domain of the function. Another way of thinking of that is no matter what point I choose, it's always continuous and connected to all the rest of the points, no matter which one I choose. That does not happen right here because if I choose this point, I am not connected to the points to the left of it. So this is a discontinuous function. So bottom line is there's a difference between a discontinuity at a point and being discontinuous. This graph right here has a discontinuity at a point, but it is actually considered to be a continuous function because at the place where it has a discontinuity, there isn't another point. Unlike this one, the difference being that I can isolate this point right here. That is a point that is discontinuous from the rest of the graph. Therefore, this is not considered to be a continuous function. All right. So here's number one, what values of x is h not continuous, and then what type of discontinuity do we have? So, I wanted to talk about the discontinuities before I do that. So there are essentially three types of discontinuities. There are removable discontinuities. A removable discontinuity is simply a hole in the graph. We call it removable because we can fix that discontinuity by simply drawing in a single point. This graph right here has a removable discontinuity. This graph has a removable discontinuity. And that's because in either case, in the bottom case, by just adding a point right there, I have filled the hole and removed the discontinuity. In the case of the graph up above it, I would move this point and put it right there instead, and I will have removed the discontinuity. I cannot do that with this graph right here because I can't add a single point and connect those pieces together. So this is what we call a jump discontinuity. So in a jump discontinuity, we have a failure of the limit to exist. It's separated by a finite amount. So one side's way up here, the other side's way down here. There's a jump. This is what we call the jump. We call that a jump discontinuity. And then when we have a vertical asymptote where one side is going up to infinity and the other side's either going up or down to infinity as well, anytime you have a vertical asymptote, we call that an infinite discontinuity. So these are the three main types of discontinuities that you need to know about: removable, jump, and infinite. All right, so now I can go on to my example. For what values of x is h not continuous? All right, so what I'm going to do here is I'm just going to graph this out. Let's do it this way. So this is a piecewise function. So at -2, it is the line with a slope of -2 and a y-intercept of 3. So just consider what happens if I were to plug -2 into there. I would get 7. So I'm going to put this up here at a height of 7. Now actually, since it's not included right there, that's not there, I'm going to use the open circle instead. So this is 7, open circle. And then this slope has a -2, so it's going to be coming down like this. And it's defined for x less than -2. So it's going to look something like that. Then at -2, the function is defined to be equal to 3. So 3 is about right there. And then after -2, for values greater than -2, it's going to be this cubic function. And I don't really know what that looks like, but I can evaluate it at -2. -2 cubed minus 6 times -2 plus 3. That is -8 plus 12 plus 3. That is 7. So the cubic function is going to have also a height of 7, and then it's going to go off and do whatever it's going to do. I don't know. So in this case, what we have is we have the limit as x approaches -2 of h of x actually existing and being equal to 7, because the left side comes in at a height of 7, and so does the right-hand side. And we also have h of -2 existing. That's equal to 3. So 1 and 2 here are satisfied, but 3 is not, because these two numbers do not equal each other. So we have a discontinuity, and this is what we call a removable discontinuity at x equals -2. All right, number 2, f is continuous and f of x is equal to this when x is not 2. That should be say -2, by the way. So we have a problem at -2. If you just try to substitute in -2 in place of x, you're going to get -2 squared minus 4 over -2 plus 2, which is 0 over 0. So we have something going on at 0 over 0. Now I know that x squared minus 4 over x plus 2 can be factored into x plus 2x minus 2 over x plus 2. And so as long as x is not equal to -2, this function right here is really just the graph x minus 2. So what the function f of x is going to look like is it's going to pass through -2 on the y-axis. It's going to have a slope of 1. And it's, let me move that up so it's more visible. So it's going to pass through -2 on the x-axis, slope of 1. It's going to go like this. Let me try to actually draw a straight line. That's better. However, at -2, something strange is going on. I get this 0 over 0. And you probably recall from your pre-calculus that when you have a common factor in the numerator and the denominator, that causes a hole in the graph. So we have this hole in the graph at -2. But they're telling me that my function's continuous. So in order to answer this question, f of -2, I have to figure out what should I define -2 to fill that hole. In the piecewise function above, you'll see that h was defined to be 3 at -2. Had we defined h to instead be 7 at -2, this point right here would have filled that hole in and made my graph continuous. That's what I want to figure out right now. What is it that we need the y value to be to fill in that hole? Well, what we really need to consider then is we need the limit, because if I can work out the limit from the left and the limit from the right, that will tell me what that y value is. I need the limit as x approaches -2 of my function f of x. Well, we can just use this simplified version of f of x. So that's really just the limit as x approaches -2 of x minus 2, which by direct substitution is -2 minus 2, or -4. So I need to define my graph to be -4, fill in the hole, and make the graph continuous. So I need f of -2 to be equal to -4. All right, which functions are continuous for all real numbers of x? Why don't we take a look at our graphing calculator? Well, let's just use Desmos. That'll be easier. All right, so I'm going to look at x to the 2/3. X. I need the Desmos. Where is the Desmos? Switch to my keyboard here. X to the 2/3. All right, so x to the 2/3. I don't see any holes or asymptotes. It appears to be continuous all the time. So that one's continuous for all the numbers. How about e to the x? I know e to the x. You should know e to the x too. E to the x is a nice graph. It's got no holes. It's got no vertical asymptotes. This almost looks like a vertical asymptote, but it's not. It just keeps going up and up and up and up. So that one's good. And then how about tangent? You probably have a vision of what tangent looks like in your mind. So going back to what I was talking about before, we consider tangent to be continuous because even though it has discontinuities, has these vertical asymptotes, the function is not defined there. So if you can pick a point anywhere on here, the graph's always continuous at that point. However, this question is specifically asking which are continuous for all real numbers. And this is obviously not continuous everywhere because it has vertical asymptotes. So it's not this one. So it's only 1 and 2. All right. And then the last question here. Another piecewise function, we want to know what values of the constant c is the function g continuous over all the real numbers. All right, so what's happening here is when we are less than or equal to 3, we're equal to some line. Now, I don't know what the slope of that line is because I don't know what c is. I'm trying to find it. But we're equal to some line. Then at 3, we change over and we are equal to some parabola. Now, once again, I don't know what that parabola looks like because I don't know what the value of c is. But that parabola could go like this, in which case I would not have a continuous function. However, if we choose c just right, it could be that that parabola will line up just like this, and now I will have a continuous function. So what I need to do is I need to figure out the value of c that's going to make the limit on the left equal the limit on the right. So I need the limit as x approaches 3 on the left of the function g to be the same as the limit as x approaches 3 from the right on the function g. In this example, that's limit as x approaches 3 from the left on cx plus 1. I need that to equal the limit as x approaches 3 from the right on cx squared minus 1. All right, well, these are nice functions, so I can just use direct substitution. C times 3 plus 1 is equal to c times 3 squared minus 1. 3c plus 1 equals 9c minus 1. Subtract 3c on both sides. 1 equals 6c minus 1. Add 1 on both sides. 2 is equal to 6c. c is 1/3. So that is going to make those two functions have a common y value at 3, which guarantees that they will come together.